When you select a compressor, you are not buying a machine from a catalog. You are defining how the plant will start, control, survive abnormal conditions, recover from trips, and remain maintainable for the next 20 years. A compressor can meet rated flow and discharge pressure on paper and still be completely wrong for the service. Real selection depends on gas composition, molecular weight, suction density, compression ratio, operating range, contaminants, liquid formation, utility availability, service criticality, and the consequences of failure. Your first engineering decision is therefore not centrifugal versus reciprocating. Your first decision is to define the complete operating envelope. What happens at minimum flow? What happens when suction pressure falls or discharge pressure rises? Will molecular weight change? Will machines operate in parallel? Can liquid condense after intercooling? Is the gas corrosive, flammable, hydrogen-rich, or highly toxic? Must the compressor restart against residual pressure? How quickly must it unload, isolate, or depressurize after a trip? If these conditions are absent from the requisition, the vendor will optimize the machine for the rated point. The plant, however, will spend much of its life away from that point. The next principle is proven experience. Do not allow your project to become a field development program for an unproven compressor, seal, rotor, impeller, control system, or auxiliary arrangement. A feature is not proven because it appears in a vendor presentation. It is proven when comparable machines have accumulated substantial operating hours under similar gas composition, pressure, temperature, speed, and loading. Novelty may reduce purchase price, footprint, or delivery time. It may also transfer technical risk directly into commissioning and operation. Every unproven feature must be declared, technically reviewed, and approved before purchase. At the same time, rationalize equipment where practical. Reducing the number of compressor manufacturers, seal designs, bearing types, control platforms, and auxiliary system arrangements can lower spare parts inventory and maintenance complexity. But standardization must never force the wrong compressor into the wrong duty. The objective is minimum lifecycle cost, not minimum equipment variety at any cost. Now consider compressor type. Axial compressors are strong candidates for extremely large flows of clean, non-corrosive gas. They can achieve high efficiency, but their operating range is narrower, their surge behavior requires careful control, and they are more sensitive to fouling. When an axial compressor ingests dirt, the problem is not merely cosmetic. Blade aerodynamics deteriorate, efficiency falls, operating margin contracts, and failure risk increases. This makes inlet filtration and online performance monitoring critical. Centrifugal compressors should normally be the first consideration when flow is sufficiently high and the duty falls within an efficient operating range. They provide continuous flow, relatively low vibration, good reliability, and the potential for long uninterrupted operating periods. But you must verify more than rated efficiency. Check the number of stages, discharge temperature, rotor stability, surge margin, side streams, seal pressure, gas property variation, and the effect of operating away from the design point. Do not simply keep adding impellers to achieve more head. Excessive staging increases rotor length, dynamic complexity, seal exposure, and sensitivity to off-design operation. If the required compression ratio drives the casing toward an impractical number of stages, reassess the arrangement. Introduce intercooling. Divide the service between casings, or select another compressor type. Reciprocating compressors become attractive when the required flow is relatively low and the pressure ratio is high. They can achieve high discharge pressures efficiently, but they introduce pulsation, cylinder valve maintenance, rod loading, packing leakage, lubrication management, and more complex piping dynamics. For critical reciprocating services, evaluate whether a standby machine is justified. The decision should come from service consequences, proven availability, maintenance duration, and production loss economics. Do not apply a spare machine automatically, and do not remove it merely to reduce capital cost. Non-lubricated reciprocating compressors should be considered when contamination by lubricating oil is unacceptable, including air, oxygen, and surfaces that may be exposed to air during regeneration. The distance piece arrangement must prevent oil migration from the crankcase toward the process cylinder. For extremely low flow at very high pressure, a diaphragm compressor may be the correct solution. Rotary positive displacement compressors should be selected only when they offer a clear duty-specific advantage. Oil-flooded screw compressors can be effective in refrigeration, tool air, and vapor recovery applications. They handle changing molecular weight well and can provide favorable single-stage turndown. Liquid ring compressors are valuable in wet vacuum service. Dry screw, sliding vane, and rotary lobe machines require proven operating experience for the specific process duty. Compact packaging is not by itself a technical justification. Integrally geared centrifugal compressors can be economical for plant air, instrument air, inert gases, and selected clean process gases. Their cost advantage comes from standardization. Every unnecessary project-specific modification reduces that advantage. Add special requirements only where safety, reliability, or operability genuinely demands them. Fans and blowers belong at the low-pressure end of the selection range. A centrifugal fan should normally be considered where only a small pressure rise is required. Do not install a positive displacement blower where a fan can perform the duty more efficiently and with lower pulsation. Once the compressor type is selected, assign complete train responsibility. The compressor, driver, gear, couplings, lubrication system, seal system, controls, and auxiliaries operate as one integrated machine. They should not become separate islands of responsibility. One manufacturer should coordinate the mechanical, aerodynamic, thermodynamic, and torsional performance of the complete train and guarantee the integrated result. When responsibility is fragmented, interface failures appear during testing and commissioning. The compressor vendor blames the motor vendor blames the starting method. The gear vendor blames torsional excitation. The control supplier blames process data. The operator inherits the unresolved system. Shaft sealing is one of the most consequential design decisions. For many hazardous process gas centrifugal compressors, dry gas seals are the preferred arrangement when pressure, temperature, gas cleanliness, and transient conditions remain within proven limits. A tandem arrangement with clean inert buffer gas provides controlled primary leakage, secondary containment, and separation from the bearing housing. But a dry gas seal is not automatically reliable. It requires clean, dry, and adequately pressurized seal gas during normal operation, startup, shutdown, settle out, depressurization, and coast down. Reverse differential pressure, contaminated seal gas, liquid carryover, or loss of buffer supply can damage the seal rapidly. Never treat seal gas engineering as an accessory package. Confirm the pressure hierarchy, filtration, heating, flow measurement, alarms, shutdown logic, flare back pressure exposure, and availability of separation gas. Mechanical contact seals may be suitable for clean gas duties and can tolerate certain pressure transients. Liquid film seals remain relevant where pressure, temperature, or gas cleanliness exceeds the proven capability of dry gas seals. Labyrinth seals are appropriate for clean, non-toxic, and non-flammable gases such as air and nitrogen, and are normally required for oxygen service. The driver must be selected as part of the process control philosophy. For centrifugal and axial compressors, speed variation is generally the most efficient method of capacity control. Variable speed electric drives, steam turbines, suitable gas turbines, engines, or fluid drive systems may be considered according to utility availability, turndown, starting requirements, and lifecycle economics. A constant speed centrifugal compressor normally requires suction throttling, recycle control, or both. Inlet guide vanes should be limited to clean, non-corrosive gas applications. For reciprocating compressors, electric motors are normally the first choice. Suction valve unloading is commonly preferred for capacity control. Variable speed operation may be considered, but minimum speed must still provide adequate lubrication and acceptable rod load reversal. Avoid control arrangements that introduce unreliable or difficult to maintain cylinder mechanisms. Testing must prove the equipment you are buying, not merely produce documents. A complete compressor driver train should undergo an integrated mechanical test unless there is a technically justified reason not to. When several identical trains are purchased, testing the first complete train may be sufficient, provided the remaining units are genuinely identical. Centrifugal and axial machines require verified performance testing. A full pressure, full speed test using a gas with representative density becomes particularly important for very high suction pressures, marginal rotor stability, multiple side streams, or an unproven compressor-driver combination. Reciprocating compressors should undergo a mechanical running test. Their capacity can often be predicted accurately from cylinder geometry, speed, and gas properties, but variable speed trains may justify a complete string test. Pulsation and mechanical response analysis are mandatory engineering activities, not optional acoustic studies. Pulsation can damage piping, valves, vessels, instruments, and compressor components, even when average pressure appears moderate. Rotary compressors require mechanical running tests, and oil-free machines should be performance tested under conditions representing expected site temperatures as closely as practical. Now, move from the vendor shop to the site, where many good compressors are damaged by poor installation. The layout must support safe operation and full maintenance. Provide access to instruments, valves, filters, coolers, seals, and bearings. Provide space to remove rotors, bundles, piston rods, cylinders, motors, gears, and auxiliaries. Confirm that platforms and floors can support the cumulative maintenance load when multiple machines are dismantled at the same time. Lifting philosophy must be decided through lifecycle evaluation. A permanent overhead crane may be justified for critical or frequently maintained equipment. In other cases, a mobile crane may be more economical. What matters is that the maintenance strategy is defined before structural steel, roofs, and pipe racks block the lifting path. Ventilation and hazardous area classification require special attention for hydrogen, flammable, and highly toxic services. An enclosed compressor house without effective ventilation can turn a minor seal leak into a major incident. Temporary suction strainers should be installed close to the compressor during commissioning to intercept construction debris. Monitor differential pressure across the strainer. Excessive differential pressure starves the compressor, distorts performance, and may collapse the strainer. Once the piping system is proven clean, remove the complete temporary strainer assembly. Do not leave it permanently because responsibility for removal was never assigned. Air compressor intake systems require equally serious engineering. Contaminants reduce efficiency, promote corrosion, and can damage axial blades. Intake filtration must reflect local dust, salt, humidity, insects, rain, snow, and industrial contamination. Locate the intake away from flammable releases, open drains, and process leakage sources. Keep it sufficiently above grade to reduce dust and insect ingestion. The ducting must be leak-tight, corrosion-resistant, and arranged to prevent rainwater accumulation. Filter housings need safe access and should permit maintenance without unnecessary compressor shutdown. For axial air compressors, high-efficiency multi-stage filtration is essential because these machines are highly sensitive to fouling. Maintain low filter face velocity and an acceptable clean filter pressure drop. A filter that removes fine particles but consumes excessive suction pressure is not a good design. Piping around the compressor must protect the machine during both normal and abnormal operation. Provide positive isolation, safe depressurization, and purging. For highly toxic service, remotely operated suction and discharge isolation with automatic depressurization should be considered as a minimum protective arrangement. Every pressure-containing section of a reciprocating compressor must be protected against overpressure. Distance piece vents must be large enough to prevent pressure buildup following packing failure. For centrifugal and axial compressors, locate the discharge check valve close to the machine to minimize reverse flow inventory. The anti-surge recycle connection must be upstream of that check valve and as close to the compressor discharge as practical. The anti-surge valve and recycle line must pass sufficient flow during rated operation, minimum flow operation, startup, shutdown, and trip transients. A valve sized only for steady state control may be too slow or too small during an emergency. If hot recycle gas raises suction temperature and reduces compressor margin, provide recycle cooling. Route the suction side tie-in so that condensed liquid cannot enter the machine. Liquid is one of the fastest ways to destroy a gas compressor. Install suction and interstage knockout facilities wherever condensation or entrainment is credible. Keep them close to the compressor. Make the final suction line short, continuously sloped toward the separator, free of pockets, and protected against condensation by insulation or heat tracing where required. Prevent discharge system condensate from flowing back into the compressor after shutdown. Provide independent high-level alarm and high-level trip functions. Do not use one sensing chain for both warning and shutdown, and then call it redundancy. For multi-stage hydrocarbon compression, calculate phase equilibrium at each interstage pressure and temperature. Intercooling changes gas composition. Liquids drop out. Molecular weight changes. Stage pressure ratios shift. These effects determine separator size, cooler duty, relief settings, cylinder selection, impeller selection, and required driver power. Condition monitoring must combine machinery data with process data. For centrifugal and axial compressors, monitor inlet and outlet pressure, temperature and flow, speed, recycle or surge parameters, shaft vibration, phase reference, axial position, bearing metal temperature, and seal performance. For reciprocating compressors, monitor stage pressures and temperatures, flow, rod drop, bearing temperature, crankcase vibration, packing leakage, and valve temperatures, with provisions for pressure volume analysis. Do not collect these values only for alarms. Store long-term trends, startup transients, shutdown behavior, and trip data. Calculate efficiency and compare actual performance with expected performance. Make the monitoring system capable of communicating with plant controls, safeguarding systems, anti-surge controls, and driver controls. A compressor rarely fails without warning. The warning is often present as increasing vibration, changing axial position, deteriorating efficiency, rising seal leakage, abnormal valve temperature, altered interstage pressure, or increasing recycle demand. The organization fails when the data is fragmented, poorly stored, or never interpreted. Finally, design for the years after commissioning. Provide online and offline washing when the gas contains salts, dirt, or unsaturated hydrocarbons that can deposit on internal surfaces. Washing liquid, atomization, injection location, drains, and compatibility with downstream equipment must be agreed during design. Consider internal coatings for severe fouling service, but verify application temperature, adhesion, and compatibility with the base material. Define strategic spare parts according to service criticality and credible failure modes. A warehouse full of low-value items does not guarantee availability. Identify the long lead rotors, seals, bearings, valves, packing sets, control hardware, and specialist auxiliaries that actually determine outage duration. The central lesson is simple. A reliable compressor installation is not created by selecting the most efficient machine at the rated point. It is created by integrating process definition, proven design, compressor type, driver, seals, auxiliaries, controls, testing, installation, protection, monitoring, and maintenance into one engineered system. When you get that integration right, the compressor starts cleanly, controls smoothly, remains away from surge, rejects liquid, survives transients, and gives operators clear warning before deterioration becomes failure. When you get it wrong, the problem may appear as a damaged seal, unstable anti-surge loop, cracked pipe, fouled blade, overloaded motor, or recurring high vibration. But the root cause usually began much earlier, with incomplete operating data, fragmented responsibility, or an engineering decision based only on purchase price. That is the difference between buying a compressor and engineering a compression system. Like, share and subscribe for more practical engineering design and implementation podcasts covering rotating equipment, process engineering, instrumentation, automation, control systems, project execution, commissioning, and lifecycle reliability.